Okay, grade 12 chemistry. This is video number 2. In this video we are going to take a bit of a deeper dive into the quantum theory of the atom, and what we're particularly interested in is the sub-levels, the sub-energy levels in the quantum model. What we're really trying to get to is understanding these diagrams here, these Aufbau diagrams they're called. That's what we're interested in. So, looking at what we're going to talk about today, we are going to talk about energy levels and sublevels. So the basic things that tell us where we're going to put stuff in this diagram. We'll talk about the pattern of orbital distributions. How do we know that there's 5 spots and then 3 spots and then 7 spots and stuff like that. I'll briefly take a detour into spin and the Pauli exclusion principle. Because that's important to explain why we can fit 2 electrons into each space, and then we'll get into the actual diagrams themselves. If we have time at the end, I'm going to talk a bit about some exceptions to the Aufbau rules, but that's not particularly important. The curriculum wants you to be able to draw electron configurations, but doesn't really have any mention of those exceptions. Okay, so let's go and start with energy levels and sublevels. And this is where we're starting with subshell theory. And what we're interested in is really getting down to the 4 quantum numbers. The 4 quantum numbers, and I'll just move my stuff over here. The 4 quantum numbers are these numbers that basically tell us the address of the electron. So I made a dumb little comic here, like the electron's address, right? You could be in shell 3, this orbital, this orientation, and then this particular spin, and it gets more specific, kind of like in your address, you have your house number, then your street, then your city, then your province, same kind of idea. So these all have numbers, and you don't really have to worry too much about how the numbers are determined. The curriculum doesn't actually mention a lot about quantum numbers, but I like to talk about them because they're frequently a confusing subject in university chemistry courses, so I thought I'd give you guys a primer. So, subshell theory. As spectroscopy got better and better, they realized that, those jumps, those Bohr diagram jumps, they were being split into subsections. Those little lines were not just one line, but there were like 2 little lines, and they were really close together, and sometimes 3 and sometimes 4. And what they worked out here was the first shell just had 1 subshell, the first shell. The second shell, though, in what they had as Bohr diagrams, actually had 2 subshells. And the third shell had 3. Guess how many the fourth shell had? Yeah, 4. Of course it had 4 shells. So that's the first kind of rule that we have, is that in the first shell there's only 1 possible subshell. In the second shell there are 2 possible subshells. In the third shell there are 3 possible subshells, and so on and so forth. Now, the details on why they're a particular color, or a particular shape rather, come from the Schrödinger equation, which we don't get into, but this is what the subshells look like. So the first subshell, the lowest subshell in every one of these, is the S subshell. The S subshell just looks like a sphere. In the 1s, remember, that's one wave around the central nucleus, one wave, and there's only one way to do that. All right, that's just a circle like that. For the second energy level, that's 2 waves around the central nucleus. So you can have a wave that's doing this, which is actually what we're seeing in the p orbital. That's the higher energy. And you can have a wave inside a wave. It's like, kind of like that. That is the 2 waves in a spherical orbital. Now, in the third energy level with 3 waves, you have a chance to do this kind of weird cloverleaf type thing, because you can fit kind of 3 waves in there. And in the 4th energy level, you can fit 4 waves on, so you can have like a figure 8, but times 2. So you end up with this weird f orbital thing. They get weirder and lumpier the further up you go. But you can also make this, you can make a 4D. They're just kind of weirder. You can make a 4P, which is also just a weird version of this, and a 4S, which is just four stacked spheres inside each other, pulsating kind of like that. Yeah, there's a really good animation of this on Wikipedia. I'm going to pause and go to the Wikipedia page, and I'll show you the animation. So here on Wikipedia, they have the S type, that's that first one, and that's like the sphere. You see that the one wave would just be a sphere up and down. But if you want two waves on a sphere, you have to kind of do that. And if you want three waves on a sphere, it looks like that. But it keeps that circular shape throughout. Now, if we look at the P type, the next one, you have, you know, the lowest energy possible thing you can have in a P type is what is the two, right? The two waves back and forth. When you get to the next level up, you can have, you know, 3 and then 4. So that's what it looks like. And then D, you end up with, you know, a more interesting resonance mode. And it gets more and more and more complex the further up you go. Now, further up in this article, they actually have a 3D model of every single orbital, which I think is pretty cool. And you can see the same thing. The S is always a sphere. The P kind of looks like, you know, a dumbbell kind of thing. And there's different orientations of them. If I zoom in here, you can see that, you know, there's I lost it. It's down here somewhere. There you go. There's like up, down, left, right, and in, out. And then there's the D orbitals, which are also just different orientations of that kind of like four-lobed pattern. And then the F orbitals are just all kinds of weird. There's all kinds of weird lumpy ones there. Okay, so that's orbitals. Now S, P, D, F is the order that they go in. So I don't know how you want to remember it. There's different ways to do it. I just remember like PDF, like the PDF files that you can find on the internet. And S is just the first one, S for sphere. Yeah, it's SPDF. All neutral atoms only use these orbital shapes, but there are higher level shapes that can be described by the Schrödinger equation, which are even more complicated. After F, it just goes on alphabetically. H, I. There's no J because that's a different quantum thing, but then it goes on after J. You know, H, I, K, L, M, N, O, and off it goes. So that's orbitals. That's subshell theory. The important thing here is that there is there's only one possibility for the first energy level, 2 for the second, 3 for the third, and so on. Here's a look at the 5 different D orbitals, 5 different D orbitals. So D only starts in the third energy level. And together, these 5 different D orbitals make up the D subshell. And there's 5 of them. 5 of them. There's only one possibility for the sphere, only one possibility for S. There's 3 possibilities for this one. There's 5 for this one. And if you want to follow the pattern, there's 7 for the F orbital. So that's the next thing we're going to talk about, is how these things are arranged. So I'm going to actually jump over to this, take away that image, and I'm going to talk about the organization of these subshells. Now the proof for this, actually we might as well talk about where the proof comes from. That's actually this picture. If I open up this picture real big, this is also from Wikipedia. This is the energy levels, the ionization energy of the electrons, the outsidemost electron in each, along the periodic table. So down here you have the periodic table. Here's the ionization energy, which is how much energy it takes to rip an electron away. And you see here, you know, hydrogen, helium, and then there's this nice even march from lithium to neon, another even march from sodium to argon. But then you get this weird, like this and then that from potassium over to krypton. There's like clearly a difference between these. Those are different subshells. This is part of the reason that they were able to describe it. And here you see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here you have 14. Right? And then 10. 14 and then 10. From there they worked out, take away that image, from there they worked out that, if you're in level 1, you can only have 1s. If you're in level 2, you can have 2s and 2p. If you're level 3, you can have 3s, 3p, and 3d, right? And so on. But then, or in 4, you can have 4s, 4p, 4d, 4f. And then from looking at this kind of stuff, they noticed that, in the p orbitals, that always seem to have 6 of them, always 6. In the d orbitals, there was always 10, and in the f orbitals, there were always 14. So these guys, there's only one of each, right? Because the sphere can only be in one orientation. These ones, you can have 3 of each. 3 of each. And that's because the barbell, those are the barbell shapes, the figure 8 shapes. You can have up and down, left and right, and they don't interfere with each other because it's like a figure 8 and the center is free. And you can also have in and out. So there's an X, a Y, and a Z kind of thing going on. So that's 1, then 3. In the d orbitals, there were 5. And in the f orbitals, there are 7 of each. 7 of them. So 1, 3, 5, 7. It's the odd numbers. There's a mathematical pattern to it. The next one up, the G, would have 9, and H would have 11 orbitals. And those are just based on which direction the orbitals are in. And then within that, you can have 2 electrons in each actual orbital. So times 2 equals 2, times 2 equals 6, times 2 equals 10, and times 2 equals 14. And that, they theorized, is where this pattern comes from, where it's 2, and then 2, and then 6, 2, and then 6. See, like, goes up and then down, and then goes up 6, and then up and then down, and then up 6. And then 2, and then 10, and then 6. So 2, 10, 6. Again, 2, 10, 6, 2, 14, 10, 6, 2, 14, 10, and then presumably 6 after that. So that's how it's organized. So those are shells and subshells, and the pattern of orbital distributions. Okay, so I'm going to pause and set up the rest of this. So give me a sec. Okay, so let's talk about the pattern of orbital distributions. So the pattern is a little bit interesting. It would be really great for quantum physics if the pattern went something like this. Here's 1s, and here's 2s, and here's 2p. And then wouldn't it be great if the next one was 3 levels, right? 1, 2, 3. And it was 3s, 3p, and then the next one would be 3d. Right? That would be wonderful, but that's not actually what happens, because the further up you go, the further you go from the nucleus, the closer the energy levels get to each other. And annoyingly, 4s just sneaks in ahead of 3d. Just sneaks in ahead of 3D. And then, what's after 4s? Well, it would be 4p. And then you've got 4d. And you'd have 4f. But the same thing happens. The same thing happens, and that's that 5s 5s actually sneaks in ahead of 4d. And even worse, 5p sneaks between 4d and 4f. And even worse, 6s actually sneaks in ahead of 4f. And so you get this really annoying, it's regular at the start, and then other shells start sneaking in as you go up. So I'm going to, using only 4 colors, because I've only got 4 colors, I'm going to try to diagram it out in full here. So let's start with 1s, right? 1s. I'll just leave the caps off so that I can use it. So 1s, and then 2s, and then 2p, and then 3s, and then 3p, and then before 3d can come in, you get 4s, and then there's 3d, and then 4p. And then we get 5s. What do I do? Red next, right? 5s. 4p. 5s. We'll want 4d now. Well, wouldn't be. Yeah, 4d. 4d. 5s, then 4d, right? 4d sneaks in ahead of 5s. Then it should be 4p, right? We've got 4p. 5s. 5p, I think. Yeah, 5p. And then it's, let's see, it's black, red, blue, green. We've done black, so I need red again. And it's 6s, which sneaks in. And at that point, all the way from back here, back from 4, we've got 4f. 4f that can sneak in. And then 4f, then finally 5d. And then 6p. And then blue before we're finally going to get it to 7. 7s. 7s. Then we'd be down to 5f, which is black. 5f, which is black. 6d. And then 7p. So if we were to kind of label them, right, here's number 1, here's energy level 5, here's number 2, here's energy level 6, here's energy level 3, and you've got and here's energy level 7. And here's number 4. Number 4 is really spread out here. Right. So in terms of energy, remember this is all in terms of energy, right? Energy. That's how we see them organize. And the proof comes from this, right? The proof comes from this thing, which shows you the energy based on the different elements, Right, so you see that all of the lanthanoids have a lower energy, lanthanides rather, have a lower energy, and then they'll come off first. Those electrons will come off before these electrons do, and stuff like that. Or will go in before these electrons do. So, with enough kind of empirical evidence, they worked out this sequence. And it's all empirical. It's all based on what they actually see, how they see electrons joining onto atoms or getting pulled off of atoms. Then they took all of that energy stuff together, and they made a table. This periodic table here. This periodic table is actually based on that sequence of energy levels right up there. Right? That sequence of energy levels up there makes this table. Because you have two here, two of them there, and the 1s orbital can only have 2 electrons in it. The 2s orbital can also only have 2. There's 2s. And then there's 6 that can go into 2p. Remember that the p orbital can hold 3 different orientations, and each orientation holds 2 electrons. So there's 6 there, 6. And another 2, that's 3s, and then another 6, that's 3p. Then another 2, that's 4s. And then from there, 3d is there now. So 3d has those 10 electrons, because the d orbital in s level up has 5 possible orientations, and each orientation has 2 electrons. So that's 10. Then 6, and that 6 is 4p. And then back to 2, and then back to 10, and then back to 6, and then back to 2, and then we get our first f orbital. The f orbitals are actually just down here in the table, but that actually kind of sneaks into there. So the table is arranged on this spectrum. So if you ever kind of get confused or you don't want to remember this sequence, which I don't even remember that sequence, I was just thinking about the table in my head, just look at the table. 1s, or 2s, 2p, 3s, 3p, 4s, 4p, 3d. One way to think about it is that the D block is actually sunk down by 1 from where it should be, because it kind of snuck in, right? 4s snuck in. Because all of these, every time you get to a new s orbital, that starts a new period. The reason that a new s orbital starts a new period is that they're big and spherical, and they kind of encompass all of the orbitals underneath them, because spheres are large, kind of thing. So every time you get to a new s orbital, you start a new period of the table. So that's why this only has a possibility for 2, this has a possibility for 8, this has a possibility for 8, that has a possibility for 18, 18, 32, and 32. This is where that guy comes from, which is always really, really interesting. Let's jump back to the note, take away that image. And this is basically what I was going to talk about. The 4 quantum numbers, we have rules for determining these quantum numbers. You don't have to worry about them too much. They do often confuse people, but it's just a way to keep track of how many shells and subshells you can have. So basically n is the shell, it's just 1, 2, 3, 4, 5, 6, 7 by definition. Then L is based on n, and it's just a way to show that you can have only 1 if you're in energy level 1, you can have 2 if you're in energy level 2, 3 if you're in energy level 3. Now you'd think that it would just be like, the number of L's is equal to that number, but because it has to go into an equation, a 3D vector equation, the first number has to be 0, because that says that's like the sphere, right? 0 kind of symmetry. It's a 0 angular momentum, we call it. Right, and then for number 2, 0 would be the sphere, 1 would be the lump. For 3, you've got 0, which is the sphere, 1, which is the lump, and 3, which is like the 4 thing, the D subshells. So it's just a way to remember it. And then you've got the 1, 3, 5, 7 pattern, 1, 3, 5, 7. And that quantum number is from L to negative L. So remember, 0 is an option, and then there's -1 and 1, -2, -1, 0, 1 and 2, -3, -2, -1, 0, 1, 2, 3. And that's where we get the shapes from in this orbital. And that's the actual equation to get those Right, so minus L to L including 0. So 0, minus 1, 0, 1. That's your 1, 3, 5, 7. You know. And MS is spin. So spin is something kind of odd. Right, spin. Spin is a magnetic property of a particle. Basically, the electron acts as a little tiny magnet. And sometimes it acts as a little tiny magnet that's pointing this way. Sometimes it acts as a little tiny magnet that's pointing this way. And you can't tell just looking at the electron. And it's not actually spinning. It's just called spin. I'm going to have a video down in the description that's really, really helpful in explaining it. But you don't need to explain to me what spin is. Just know that spin can be plus or minus 1/2. Or spin, we call it spin up and spin down. Because, you know, that's just a general... just something that physicists came up with, and it was easy to refer to them as spinning up or spinning down. Really, when an electron is created, you don't know if it's spinning up or spinning down, and they can change spins too, so it's not a big difference. Now, why do we care about these numbers, and why have all these rules? Well, the numbers and the rules for writing the numbers are from the Schrödinger equation, right? If you have a different set of rules for writing them, you don't get these shapes, and we know that they take those shapes. So the actual kind of possible values here are just so that the formula comes out with the right shapes. The math formula comes out with the right shapes. But practically speaking, the existence of the numbers is due to the Pauli exclusion principle. No two electrons can have the same quantum numbers, because if they have the same quantum numbers, they're the same electron, and they would interfere with each other. But if you have two different quantum numbers, that's fine. You can basically be in the same place at the same time, as long as there's no forces trying to pull you apart or anything like that. So yeah, the two electrons can't have the same quantum numbers, and that's where we get the electron's address. So hopefully now this comic makes a little bit more sense with the plus 1/2, 1, 1, 3 kind of thing. Right? It's just a way for us to put a specific electron into the Schrödinger equation and figure out what electron cloud it's going to make and what energy that cloud is going to have. So very useful, but a little bit beyond the reach of grade 12 chemistry. Here's a little diagram I made to summarize it. We have the shells, 1, 2, 3, and 4. Then there's the subshells. Shell 1 can only have the round subshell. Shell 2 can have the round one and the lumpy one. Shell 3 can have round, lumpy, and like cloverleaf. Shell 4 can have round, lumpy, cloverleaf, and I don't know, star, whatever. But yeah, you kind of hopefully understand that. Shell 1 can only have S, Shell 2 can have S and P, Shell 3 can have S, P, and D, Shell 4 can have S, P, D, and F. And then S, P, D, and F, each S can only have one arrangement because it's a sphere. Each P can have 3 arrangements, up, down, left, right, and in, out. Each D can have 5 arrangements, each F can have 7, and then within that you have 2 electrons, right? So an up and a down electron, because an up electron and a down electron can be right next to each other, and they don't really mind each other's presence too much. So that's this diagram is a really good kind of summary of the whole thing. So in terms of energy, right, these are different energy levels. These are the same energy because they're just a different orientation, right? Whether it's like this or like this or like this, it doesn't matter. It's the same energy. But these, because they're different shapes, are different energy levels. That's something else to keep in mind. Right, so subshells have a particular energy level, but orientations of the subshell have the same. Right, and here's a diagram of that overlap, the same kind of overlap that I'm trying to show over here. Now you should be able to understand this a little better. SPD, SPD, SPDF, right? SPDF, 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 SPDF. We also often put the number in front of it, so this would be 1s. This would be 2s, right? This would be 2p. This would be 3s. Oop. You know, this would be 3s and 3p and 3d and 4s and 4p and 4d and so on, right? So we can also write them out like that, 4p and 4d. And this is actually organized in order of energy. So you can see here what I was trying to diagram earlier, that the 3s sneaks in between, that the 4s sneaks in between 3p and 3d. So 4s is a lower energy. Electrons would rather be there than there because it's lower energy. Everyone wants to be low energy, right? So that's that. Then that leads to Hund's rule. Hund's rule basically says that, and I'm gonna write this, electrons are lazy first, but antisocial second, right? What I mean by that is the way that they fill in is first they'll look for the lowest energy level because they're lazy. Lowest energy level. So let's put, the first electron might be an up electron that goes into 1s, an up electron 1s. And the second electron has a choice, right? It could go to 1s or go to 2s. Well, it's lazy first. It's lazy first and wants the lowest energy. So it'll go into 1s and join this other electron. It'll be a down electron now. By convention, we write up electrons first and then down electrons after. We don't actually know what spin they are. So then the next electron, it missed its chance to get into 1s, but 2s is right there. That's still lazy enough. It can go there. And the second electron, same thing. It's going to go to the lowest energy level. So that's the fourth electron. Now the fifth electron, 1s and 2s are full, but it'll go to 2p. But the sixth electron now has a choice. It either has an open orbital in 2p, or it can go buddy up with this electron that's occupying this orbital in 2p. And that's where the second part of Hund's rule comes from. Second part of Hund's rule says that they're antisocial second. So instead of going next to this one, it'll take up its own orbital because that is slightly lower energy than being paired up with this guy. Just a tiny bit lower energy, but enough to make it go into that orientation instead of that. And then this one will obviously go in there. My analogy for this is when you're like trying to catch the bus, you're obviously going to get on the first bus that has room for you. But then when you're on the bus, right, everyone on that bus has the same energy, right? Everyone on that bus is on the same bus. You're going to look for empty seats in your bus. So the electrons kind of do the same thing. They don't want to sit next to some weirdo on the bus. They're gonna go into singles first, and then they're gonna pair up like that. So that's Hund's rule. That's how we apply Hund's rule. And this is called an Aufbau diagram. Energy goes up, and we fill in electrons bit by bit, depending on how many electrons are in our atom. So these diagrams tell us which level is going to go next. So the next level is 3s, then higher up is 3p, and then after that 4s because it's the lowest energy, right? That's the next bus. That's the next bus. And then 3d is after that. So that's Hund's rule. Let's talk about Aufbau diagrams now and predicting Aufbau. So Aufbau diagrams, and I'm going to pause. Okay, so we're going to talk our last topic, unless we have enough time to get to the exceptions to the Aufbau rules, is predicting the Aufbau. And here's the general rule. Here's a rule that works pretty well. It's called the N plus L rule, or the Madelung rule, or the Janet rule, or the Klachowski rule, or the diagonal rule, whatever you call it. You write out your orbitals like this: 1, 2, 3, 4, 5, 6, then 1s, 2s, and 2p, because that's the only possibilities: 2s, then 2p, 3s, 3p, and 3d, then 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f. There would be a 5g here, right? Well, we might as well put that in here. Let's put 5g in here. 5g. All right, and that would be a 6f, and a 6g, and a 6h. And a 6h. And then down here you'd have 7s, 7p, and 7d. And then this diagonal rule says that the elements will fill in the orbital like this diagonally. So 1s first, then 2s, then 2p, and then 3s, and then 3p, and then it predicts 4s ahead of 4d, which is what we actually see in the periodic table. Right? It's 4s ahead of 3d rather. 4s and then 3d. So you see this one actually shows you that it kind of loops around. That's the diagonal rule. And this is the way that it goes. So 5G currently, as far as the periodic table is concerned, is not used. Neither is 6F or 6D or 8S or any of that. The periodic table ends at 7P. Furthermore, every time you get to a new S orbital, you end up with a new period. So periods start, if we were to draw it, every time you get to so there's hydrogen and helium, right? Hydrogen and helium. Then you've got, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. There's the next one, right? Before you get to 3s, that'll start the new one. Then blah, blah, blah to argon, start the new one here. And then so on and so forth, right? So that's where you draw the line of a new period on the table. So the last one that we know is Oganesson, element number 118, and that's as far as that gets. Whatever the next one is would start 8s, right? Whatever the next one is would start 8s. This is not 100% accurate. It fails to predict about 12 of the elements, but it's pretty good. So if you ever want to write out an Aufbau diagram, if you want to make one of these, if you want to make one of these diagrams, you can use the diagonal rule. Or, better yet, we always have one of these available to us, right? We always have a periodic table. Just use the periodic table, right? This is number 1, it's in 1s. This is number 2, it's in 1s. This is number 3 and 4, they're in 2s. 5, 6, 7, 8, 9, 10, 2p. 11, 12, 3s. These guys, 3p, then 4s, 4d, 4p. Now, your table isn't going to have these on there, so you have to remember some things. Things that you can remember are, every time you start a new S, you start a new period. So this is the S block. That's the S block. And helium's part of the S block, but it's over here with the noble gases because it kind of belongs better there by properties. In green is what we call the P block. Right? It's the P block. The last electron is in the P orbital. So this is the P block. It's at the same height as the S block, right? Because this is 1s and that's 2s and that's 2p, 2s, 2p, 3s, 3p. Then there's the D block, and because the 4s sneaks in ahead of 3d, this means that the D block is basically like it. If it made sense, if it was arranged kind of logically, the D block should be there, but it is sunk down by 1. Sunk down by 1, right? So it's 4s and then 3d. 4s then 3d on your table. 5s would go to 4d. 6s would go to 5d. And so on. And then the F block gets it even a little bit worse because it is sunk down by 2. Right? If it was in the right place, right, it should start there. Right? It should start there, but it's actually starting there, right? Sunk down by 2, down by 2. And that's where the F block sits. So that's one way to remember how these things go. You just look at your periodic table, or you can use the diagonal rule. That's how you would predict it. Right? And then that'll help you draw something like this. Okay, we have here 1s, 2s, 2p, 3s, 3p, 4s. Right? There's the next one, 4s after 3p because it's not 3d, and then 3d, 3p, and so on and so forth. So this is sulfur. It's sulfur's electron diagram or Aufbau diagram. They're called electron arrangements. Aufbau, by the way, is a German word that means filling up. So Aufbau diagram literally means filling up diagram. So that's that. And then you can use your table to figure them out. And this is the the way to write them out, write out an electron configuration. So you see 1s, and there's 2 electrons there. 2s, there's 2 electrons there. 2p, there's 6 electrons there. 3s, there's 2 electrons there. 3p, there's 4 electrons there. So that's how you would create your own Aufbau diagram and how you would fill it up with electrons. And note that Hund's rule is still in effect. Electrons are lazy first and antisocial second. Look at 3p. The electrons have spread out first to put 1 electron into each of the orbitals, and then the next electron, having nowhere else to go, has partnered up with this electron here. Yeah, so that's Aufbau diagrams in a nutshell. There's also a shortcut that you can take, because every time you get to a new s orbital, it becomes a noble gas. So if I just if I draw a line here, let me just draw a line. So that's hydrogen and helium. Everything before 3s is everything up to neon. Everything before 4s is everything up to argon. So there's a shorthand you can take where this is helium. Helium. Oh, I'm going to make this green. Let's make that green. Helium. Let's make all of them green. Helium, neon, argon. All right, argon, and then after that, krypton and xenon. You can actually use them to make a shorthand for these arrangements. You can say it's neon because we know neon is full, and then after neon you can start making this arrangement. So that arrangement can also be written as neon in square brackets, and then you go right to 3s. The 3s has 2 electrons in it, so it looks like 3s2, and then 3p, 4 electrons in 3p. So that's a quicker way of doing it compared to putting all of them together. That's how you write an electron arrangement, that's how you predict an Aufbau, and that's how you make an Aufbau diagram. We're going to get a lot of practice with this during the class session, and so yeah, I'll see you guys in class for lots of Aufbau practice. I think that's everything I had. Yeah. It's a bit of a long video, so I'm not going to talk about the exceptions. They're not in the curriculum anyway. The exceptions happen in the transition metals, and you can actually kind of see the little bump here. See the little bump? That's copper. That's one of the exceptions. Then there's this other little jump here, which is another exception when you get to the F block and D block and the way that they interact. But you don't have to worry about it. You just use these rules that I showed you. You know, specifically the Madelung rule or the diagonal rule, this guy, and you'll be able to predict it no problem. Or just use your table. In your table, that works too. So hopefully now you know how to do these, and we're going to get practice in class. Thank you very much, and I'll see you in class tomorrow.